my name is Edwin Yang. Today, I am glad to introduce our work, GPSKey, GPS-based secret key establishment for intra-vehicle environment. This research is accomplished by me and my advisor, Dr. Song Feng. Our research is about establishing secure communication channel between the devices brought into the vehicle. Nowadays, GPS receivers are highly popular and increasing number of smart devices are brought into the vehicle. However, manually pairing them can be tedious and some devices may lack of interface for pairing. How to establish a secure channel between the smart devices has been a popular research question. The recent studies propose context-based pairing schemes where the legitimate devices utilize common environmental observations to derive the secret key. The devices can utilize acoustic, wireless, brightness, visual channel, or event timings. However, as there may not be sufficient events, the existing schemes take long pairing time. Also, in order to utilize the environmental changes, additional sensors are required for the devices. Furthermore, some schemes require the user to manually trigger events, which may raise usability issues. There are context-based schemes for vehicular environments as well. They utilize inertial measurement unit, IMU, sensors to generate secret key from the vehicle's movement. However, the IMU-based schemes have several limitations. First, the devices must be strictly fixed on the vehicle. Also, the IMU sensor data are usually not considered as sensitive, thus they are not permission protected. Considering these limitations, we aim to develop more robust pairing scheme. We focus on GPS data, which are less affected by device movements and permission protected. The key idea is that the GPS-enabled devices in the same vehicle would obtain similar driving data, therefore they can derive the same secret key. We assume that two GPS-enabled devices are located in the same vehicle. We assume that the attacker cannot be in the same vehicle during the key generation because the vehicle provides the physical security boundary. Instead, the attacker launches two types of passive attacks to obtain similar GPS data. By driving other vehicle, the attacker follows or leads the target vehicle while collecting the GPS data. GPSKey consists of three phases. In the first step, we deal with missing GPS samples by performing interpolation, and then we remove noise from the GPS data. Next, we determine the starting point of key generation and exclude driving periods that may not present enough randomness. Finally, we extract secret bits from the processed GPS data and perform reconciliation to handle bit mismatches. The data pre-processing phase aims to obtain more accurate GPS data. As commercial GPS devices can obtain null data samples, we perform linear interpolation to compensate the missing data points. Next, we apply low-pass filter to remove high-frequency noise. After the first step is completed, we extract driving periods that present enough randomness. First, as vehicle at too low speed may not present enough randomness, we apply a threshold to GPS velocity. When the velocity exceeds the threshold, we utilize that timestamp as the starting point. Meanwhile, the vehicle can stop or move at the constant velocity. We first detect stopped period by utilizing GPS velocity and GPS coordinates. Next, we also check if the vehicle is moving at constant velocity by monitoring variance of velocity in the time window. The redundant periods are removed from the key generation process. In the last step, we extract secret bits from GPS data. We utilize dynamic threshold to perform quantization. We compare mean velocity and each data point within the fixed time window as shown in the figure. Since the legitimate devices may not obtain the same secret bit stream, we perform reconciliation. We utilize an existing technique, secure sketch, which consists of two functions, namely sketching and recovery. As shown in the figure, one party generates a sketch and shares it over a public channel. The other party then can utilize this shared sketch to correct bit mismatches. A secure sketch relies on error correction code. Error correction code consists of message and parity bits, which can correct limited number of bit mismatches. Let two legitimate parties, Alice and Bob, obtain highly similar bit streams W and W prime. Alice first generates a sketch S using sketching function. The sketching function shifts the bit stream W by a random error correction code C. Next, S is sent to Bob, and Bob performs recovery process with his bit stream and secure sketch S. In the recovery process, Bob first computes C prime by shifting his bit stream back by sketch S and then attempts decoding C. If the difference between W and W prime are small, Bob would get the same key as Alice. However, an adversary Eve would fail to get C because her bit stream may not similar as Alice or Bob. We perform experiments using commercial GPS-equipped devices under real-world driving environments. The user drives a standard compact vehicle on urban and rural roads. For attack experiments, an adversary drives another vehicle with a GPS device. We assume a strong attacker who applies the optimal time delay to compensate time offset caused by stalking or leading attack. We first investigate if different device types and distances between different devices affect accuracy of GPS data. We place different devices at different locations as shown in the figure, and we do not control orientation or movement of the devices. We perform 100 times of the experiment and measure similarity between the GPS data collected under legitimate and attack scenarios. As we can see in the figure, the legitimate devices achieve high similarity while the attacker fails to obtain similar enough GPS data. Interestingly, we see that the driving data collected by smartwatch are very accurate, although the driver constantly moves his hands during the experiments. We evaluate key generation performance with different quantization parameters and key sizes. We can see that GPSKey achieves about 1.7 to 1.9 bits per second, while the legitimate devices experience up to 7% of bit error rate. Meanwhile, we quantify bit error rate under two attack scenarios. Both stalking and leading attack present at least 44 and 54% of bit error rate. And we can see that the attacker fails to obtain the legitimate key. Now I conclude this presentation. To sum up, we utilize GPS driving data as source of secret key for secure intra-vehicle communication. We perform extensive experiments to evaluate feasibility and robustness of GPSKey. Finally, we demonstrate that the attacker who launches passive attacks cannot obtain the secret key. Thank you for listening. Now I will be happy to answer your questions.